Section 13.3. Multiplicative congruential generator. A multiplicative congruential PRNG uses two parameters, a multiplier m and a modulus p. Starting from the seed s, the sequence of pseudorandom numbers xn is generated by the recurrence. In other words, to get the next pseudorandom number, you multiply the previous number by m and then take the residue modulo p. The seed may be any integer 1, 2, 3 to p minus 1. The modulus p is almost always chosen to be a prime because primes produce the longest periods. The choice of p often depends on the size of the registers in the computer you are using. For 32-bit registers, the prime 2 to the power 31 minus 1, which is 2,147,483,647, is a common choice. The first PRNG in this class was published by Berkeley number theorist Derek H. Lehmer, not to be confused with Berkeley number theorist Derek N. Lehmer, his father, in 1949. The multiplier m must be chosen carefully. The period of a multiplicative congruential generator can be any integer that evenly divides p minus 1. Since p is a prime and presumably far greater than 2, p minus 1 will be even, so a very poor choice of m, such as p minus 1, could give a period of 2. A multiplier that has the maximum possible period, namely p minus 1, is called a primitive root of p. That means m, m squared, m cubed, up to m p minus 1, all have different residues modulo p. For a multiplicative congruential generator, it is best to make m a primitive root in order to get the longest possible period. Fortunately, this is easy to do. On average, just slightly less than 3/8 of the numbers in the range 2 to p minus 2 are primitive roots of p. The exact ratio is called Artin's constant, for Emil Artin, an Austrian mathematician who escaped from Nazi Germany in 1937 and finished his career at Princeton. Its value is about 0.373956. If you can factor p minus 1, then it is easy to test whether a given multiplier m is a primitive root of p. We know that the period of m must divide p minus 1, so begin by factoring p minus 1. Suppose the distinct prime factors of p minus 1 are a, b, c, and d. Then you only need to test m to the power of p minus 1 over a, mod p, m to the power of p minus 1 over b, mod p, m to the power of p minus 1 over c, mod p, and m to the power of p minus 1 over d, mod p. If none of these are 1, then m is a primitive root. For example, if p equals 13, the distinct prime factors of p minus 1 equals 12 are 2 and 3, so you only need to test exponents 12 over 2 and 12 over 3, that is, m to the power of 6 and m to the power of 4. For example, 5 is not a primitive root of 13 because 5 to the power of 4 equals 625, which is congruent to 1 mod 13. There are efficient ways to compute m to the power of x by taking successive squares. For example, to compute m to the power of 21, you could successively compute m squared, m to the power 4, m to the power 8, m to the power 16, m to the power 20, m to the power 21, using just 6 multiplications. You can get further efficiencies by using these products to compute the next power. For example, if the next value to test were m to the power 37, you could compute m to the power 32, m to the power 36, m to the power 37, using just 3 multiplications. It is more efficient to calculate the residue modulo p after each multiplication than to compute the huge number m to the power 21 and take the residue at the end. There are more sophisticated schemes that use somewhat fewer multiplications, perhaps 10% to 15% fewer, but if you are doing this only a few times, the extra effort is not worthwhile. If you are using a multiplicative congruential PRNG, it is important to know that it is the magnitude of each number that shows random properties. To convert an output R of the generator to an integer in the range 0 to n-1, the correct calculation is floor of Rn over P, where floor of x means x rounded down to the next lower integer. For example, floor of 27 is 27. Floor of 27.999 is 27. The expression floor of Rn over P is slightly biased towards smaller values, that is, it will yield lower numbers slightly more frequently than higher numbers. However, when P is much larger than n, say P is greater than 1000 n, this will not matter for cryptographic purposes. Historical aside. Incidentally, the notation floor of x and the corresponding symbol red seal of x, which means x rounded up to the next higher integer, so seal of 27.001 is 28, were both invented by Kenneth Iverson, the creator of the APL programming language, in 1962. APL was the first interactive programming language. Computer users today take interactivity for granted. You press a key or click the mouse and the computer does something. They do not realize that this concept had to be invented. Before then, the standard model for computing was that you ran a card deck through a card reader, the computer printed the results, and a few hours later you got a sheaf of paper. Warning: do not use R mod n as your random number. R mod n can be severely biased towards low values. For example, if the modulus p equals 11 and n equals 7, then the 11 possible values of R mod 7 are 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, so that 0, 1, 2 and 3 are generated twice as often as 4, 5 or 6. A multiplicative congruential generator will have decent random properties as long as m is greater than the square root of p. It is best if the multiplicative inverse m' is greater than the square root of p as well. This means that the number of bits in m needs to be at least half the number of bits in p. You want p to be as large as possible, so the generator will have a long period, and you want m to be large so the generator is random. How big can you go? The sizes of m and p are limited by the size of the registers in the computer. If you go bigger than one register, you will pay a penalty in speed.